Hello students. Today we will start completely a new area, and the discussion will be on the very important activity in the receiver, which is called synchronization. And related to the space spectrum communication system, synchronization plays a very major and a crucial role in the receiver design. Synchronization means mainly the alignment of the locally generated PN code with the code that is getting superimposed and transmitted from the transmitter. Synchronization also involves the carrier synchronization. So, please remember, for conventional communication system, when we talk about synchronization, that talks about either the time synchronization or the frequency synchronization, or the phase, also the phase synchronization. But in the space spectrum communication system, the term synchronization is related to two different aspects. One is the code synchronization, another is carrier synchronization. In conventional communication system, the synchronization is only related to the carrier synchronization, and in space spectrum communication system, the synchronization consists of code synchronization as well as carrier synchronization. When we are talking about the synchronization, we are more interested to learn first about the code synchronization process, which is fundamentally the alignment of the locally generated PN sequence code to the code that is transmitted and it is superimposed and transmitted from the transmitter, superimposed on the actual data and transmitted from the transmitter. Remember, this code synchronization is having two major parts. One is the code acquisition and another is code tracking. Today, code acquisition is the very first part of the code synchronization. Today, we will learn how code acquisition is done inside a direct sequence receiver. Today the topic will be the understanding the fundamentals of this code acquisition mechanism in the direct sequence receiver. As discussed earlier, that code acquisition, code synchronization as well as the code acquisition is a very critical block that is residing inside the receiver, and it is a very important signal processing block inside the baseband receiver that needs to be devised and needs to be designed critically. And by means of synchronization and the code acquisition, we are actually defining the generating code acquisition is having basically generating by is accomplished generating by the local replica of the PN code inside the receiver first of all, and then multiplying it with the incoming signal, which consists the PN code transmitted by the transmitter. And after this multiplication, when this multiplication is going on, remember that you have to synchronize the locally generated PN code with the incoming signal code, and then actually the desired dispersing process can take place. So, the synchronization, the term which I already told, that local, it is not only just multiplying the incoming signal with the locally generated PN code, you have to multiply with the synchronized PN code, locally generated synchronized PN code with the incoming signal to make the dispersing process faithful. And hence this synchronization will have two main parts. One is the PN code acquisition as well as, and second part is the PN tracking. Today we will enter into PN acquisition, and if you look into the PN acquisition, then we will see the whole synchronization process as a two part mainly. One is actually the coarse synchronization, another is the fine synchronization. In the coarse synchronization, the first task is to there are two PN signals right now in our hand, right. One is the incoming signal, which is coming say the RT. Another is our locally generated PN sequence. So, we are trying to synchronize the PN code inside the RT and the PN code that is locally generated. So, in the process of this synchronization or this alignment, it is not possible that at the first round you can synchronize both of them 100% perfect fashion or with a very minimal error. So, we do it in two steps. The first step that we do is called the coarse synchronization, and this coarse synchronization means that you are trying to align this both of this P and code within a small fraction of a chip duration. So, at least within the chip duration we try to align them, and if possible you try to align them within at least half of the chip duration. So, that means actually the remaining residual error should be less than equal to the chip duration T c, or always should be the less than equal to T c. So, if the it depends upon the complexity and the algorithm you are designing for the coarse synchronization in the coarse alignment process, during coarse alignment process, based on which actually it will be defining whether you will be within actually whether you are synchronizing within exactly with the residual offset of T c period or within some of it, I mean some part of it. So, you could synchronize within half of the T c period, 1/4 of T c period, or actually you are left with the residual error of full T c period, what exactly you are living with. So, error can be something like this. Suppose this is the incoming RT signal and this is the received PN chip. Suppose we are doing, and what is the target? So, let us do once more. Suppose this is the incoming signal, and suppose this is the receiving signal, locally generated PN sequence. So, this is the incoming PN code and this is the locally generated PN code. And what I mean to say by the synchronization and the offset, it's actually this of aligning this locally generated PN code with that of the incoming PN code. So, this look at this picture, the offset may be of multiple of the chip duration plus actually some fraction of the chip duration also. It depends actually on the coarse alignment process. At least we try to correct the multiple of the chip duration, and within a chip also we try to correct at least up to some level. But whatever the residual error we are left with, then we will try to acquire it by a continuous observation process, which we call it is a PN acquisition, or it is called the tracking. So, coarse estimation, when we are trying to align both the codes within the multiple of the chip duration and within a fraction of the chip duration also, I mean it should be a n times of T c plus actually some part of within T c, at least a half part of the T c period. Then we call it is a coarse estimation and coarse synchronization going on, and also we call it a PN acquisition going on. It is a coarse alignment we have done. And once the coarse alignment is achieved, the coarse aligned signal is fed to another circuit, where actually the continuous tracking of this estimated phase offsets are going on, and continuously there is a trial and continuously there is a trial going on to realign the remaining offsets or to mitigate the minimal remaining offsets within the chip period, and we call it PN tracking. And it actually, remember this PN tracking always actually is having a closed loop operation which tries to maintain the waveform, locally generated waveform, to be best possible aligned with the received signal. So, any changes in the received signal that happens because of the Doppler effect or because of the change of the delay spread inside the channel, and because of other issues that are coming from the wireless channel, and change of the speed of the velocity, change of the velocity of the vehicle also. So, from all that actually whatever the coarse alignment you are doing, it may be sufficient, but the residual error portion may keep on changing, and you are by continuously observing and assessing, measuring this remaining offsets within the chip and trying to correct it, and when the locally generated waveform is going on, local waveform is getting generated, to correct the phase of that and trying to best possible way to align it with the incoming signal is called the tracking. So, we understand now that the synchronization means the combined effect of this acquisition plus tracking, which is a coarse plus fine, and you have to do the coarse alignment first and then you enter into the fine alignment track. So, let us enter into the available literature, going through the available literature, what are the different procedure that people follow. Remember this, if you try to follow the structure of this PN acquisition systems, you will find that usually the different methods whatever is proposed, they consider a common type of the system model. This acquisition technique will consist of basically first a multiplier, where actually you will take the two different signals, one is locally generated, another is incoming, and output of this multiplier, or basically this multiplier is nothing but a correlation going on between the two, and we try to see actually the difference of the correlation, and then it's followed by a detector circuit, and output of the detector circuit is fed to a decision device or some strategy device, which actually this detector followed by a detector and the strategy decision detection and detector and decision can be combined also in some cases. And this correlation measure, based on this correlation measure and based on some decision rule, based on most probably in most of the cases based on some threshold set decision rule, we try to find out actually how big this correlation difference is there in between these two signal, whether it is good or too high or too low, and what to do next with this difference value of the correlation. And hence the strategy comes into the picture, that what to do, how to devise the algorithm based on this decision output. And difference of the schemes in the acquisition model, we will see the difference is coming due to the design of this detector, due to the change of this detector architecture. The way you are choosing this detector, that is actually devising the different kind of the PN acquisition model. And also the search mechanism based on which the decision is going on. So, that search mechanism is also playing a very important role to vary from the one code acquisition mechanism to the next code acquisition mechanism. So, we will first look based on the detector how the classification came in the PN acquisition systems. The classification will be mostly based on the coherent detection is going on or a non-coherent detection going on. For direct sequence space spectrum systems, we prefer to go ahead with a non-coherent detector. Remember why? Because we assume that carrier, I told that code synchronization and carrier synchronization are two different process that combinedly consists the synchronization in the space spectrum communication system. While we are dealing with the code acquisition and the code synchronization, we assume that the carrier synchronization is not done. That's why we don't know actually. We don't have any information about the phase of the carrier frequency, and hence it is preferable, once you don't know anything about the carrier phase and frequency, and then hence it is preferable to go ahead with the non-coherent kind of the detectors. But however, some of the code acquisition system models are there and the mechanisms are there, where actually which can estimate a priori, either they have the a priori knowledge or which can estimate also the phase values or estimate the phase of the carrier frequencies. And in such a situation also actually the coherent type of the detectors are applied. So, we will prefer to go ahead with the non-coherent detectors, and inside the non-coherent detector we will find that basically the architecture would look like this. The incoming signal will be entering into after some band pass filter. After some band pass filter, you will see that he is entering into a square law detector, and the square law detector output is entering into a integrate and dump circuit. It is integrate and dump circuit, and output of this integrate and dump circuit will be entering into a simple threshold detector, where and remember, output of the integrate and dump circuit, there will be a sampler, and it is coming to the threshold and threshold detector. And this is the combined architecture, the way the non-coherent type of the detector work. And instead of this band pass filter, if I am coming to the coherent detectors, you will get a low pass filter, and which is basically maybe constituted of integrate and dump circuit also, and then very simple either base detector or some threshold detector will be there in the path for the detection process. This portion we have already discussed why we are preferring the non-coherent detector. It is mostly common coming into the practice, but as I have already told that some of the advanced acquisition system, they may be capable of intelligent enough to estimate the carrier phase frequency shifts that are coming up dynamically, actually, that are changing because of the propagation delay as well as the Doppler, and they are capable to estimate that, and in such situation we prefer to go ahead with the coherent detector. Next slide, we will see actually the coherent detectors, and I told that in the case of coherent detector, you will have, it will be employed simply by a low pass filter, and this low pass filter you can implement by integrate and dump circuit, and output will be a simple detector like your optimum base detector, or you apply a simple threshold detector also sometimes, and here is the decision device at the output. So, first classification that we have learned now based on the detector architecture, and the detector architecture may be of coherent or non-coherent. So, based on that, actually one classification of the PN code acquisition circuits are coming up. The second classification can come based on the integration time that you are using inside the detector and integration time that you are using inside the detection and decision process, and that integration can be of over the either fixed integration time you are involving with, or you can have a variable integration time involved in the process. Fixed integration time can be further having two different types, either it is a single dwell time or it is a multiple dwell time. So, this integration time we call here the dwell, and this is basically the time duration that is involved, and if we see that the time duration over which the integration is running is one time, then we call it a single dwell time, and multiple such integration and taking the decision over the multiple such integration process is involved in the multiple dwell time. So, the fixed integration time detectors, where the integration time is fixed over which the integration and dump circuit is working, that integration interval is fixed, but it may be a single time integration or it may be the multiple time the stuff is going on. Based on that, it is a single or multiple dwell time detectors. And see this single dwell time, when actually we are using it further, actually this single dwell time detectors can be further classified based on the fact that whether you are using the full period of the code, means full time period of the code for the correlation, or you are using a part of that time period of the code for the correlation and taking decision based on the partial observation of the code duration. And based on that, it is either full period code correlation you are taking, or you are taking a partial code correlation, and hence the single dwell time also can be classified further. And see, multiple dwell detectors, they will be varying from one to another based on the fact that how you are relying on the, how you are varying the further decision over the second and the third dwell times based on the observation of the first dwell time. So, anyway the multiple dwell detectors are taking the decisions and complete observation and decision strategy over the single dwell time, and based on that observation they are taking the devising the algorithm how to behave, how much extra information needs to be extracted from the second or third or fourth dwell times. You may actually imply some kind of the logic of averaging actually all observations over the multiple dwell times and give the same weightage on the decision process independently that is going on each and every dwell time, or you can actually devise some algorithm thinking that if the single dwell time output is really very nice, then the second or third real outputs will just be utilized, one or more, two more will be simply utilized over the partial code time. Maybe it can be something like this. In the single dwell time, you can run the correlation over the whole period of the code acquisition and taking a decision, and that if you can detect actually the phase very nicely, then in the second dwell time you can reduce the length of the correlation period. Hence, that is a multiple dwell going on, but the period of the correlation is not same compared to the single and the multiple, and that decision is based on the observation of the first dwell time, whatever the estimation on the phase you are getting. And so, the multiple dwell detectors can have the several kind of the logics on how you are using the estimation of the other dwell times, rather other dwell times except the single one or the first one. And the detector structures make some decision that their interest actually may be weighted over the multiple dwell observations. And if the threshold, basically as I told that they are estimating the phase and they are trying to see whether that value is crossing some threshold or not, and based on that the decision is locked, whether synchronization has achieved or you have not synchronized, the decision is locked. And so, there is a algorithm running actually at the output of your detector and the decision device, inside the decision device at the output of the detector, which is a verification algorithm. Basically, that verification algorithm, the detector is measuring, right, the correlation difference between these two, and then the output of the detector is getting measured with a threshold value, predefined threshold value. And decision device is saying that over multiple dwell interval, how many times actually you are crossing that threshold. So, decision device, this verification algorithm says that whether you will take the decision based on the single observation, if it is a single dwell system, or you will take the further decision whether the synchronization will be declared to be achieved by observing the multiple observation over the multiple dwell time and running the verification algorithm basically over the multiple dwell time. One may run actually verification algorithm in such a way that there is a search going on, right, that how many times the difference has crossed the threshold value or it is below the threshold value. And once actually this search is going on, where to lock. So, search and lock, that two simultaneous process is involved when the verification algorithm is going on. So, you search and you then lock, devise a logic based on which the locking will be there to declare that hence the synchronization is achieved. This verification algorithm, whatever is existing in practice, as I told it, they are having multiple way or approach to declare the synchronization. One is the search and lock strategy that just now I have explained, that which takes that decision that it is locked if the majority of the times the difference is crossing that threshold level. And multiple dwell acquisition system, they locked actually either seeing that any one of the dwell time, in any one of the dwell time it output fails to cross the limit, he will declare that synchronization is not achieved. So, it depends actually upon the criteria that you are setting, how actually well, how fine you are in the achieving the synchronization. Are you designing a system which requires 100% or 99.99% say code acquisition, that much perfection is required for the design, or you are designing a system where actually the synchronization of say around 90 to 92% is okay to go ahead with. So, 90 to 92% kind of stuff can be achieved by the search to lock strategy. If you are really worried about the 99.9999% of acquisition in some kind of the system design, then you have to actually be very strict on this kind of the multiple dual acquisition systems kind of. And finally, for all these different kind of the category of the variable integration time detectors, it is reserved for those cases where actually the dwell time can be continuously be varying. For variable integration time detectors, you can actually vary the integration time of the integrate and dump receiver on the fly, and hence it is a stochastic process, and the choice of this integration time itself is a stochastic process, and hence the whole decision, how many times the decision is the correlation difference is crossing the threshold, that is also a random variable. So, completely a very good example of this variable integration time detector is that is used in the radar signal processing, and that is a very nice, very good example of this is sequential, classical sequential detectors. And next classification of the detector from here onwards, depending upon the how fast you are acquiring the code acquisition, and that means actually how fast your detectors are running. The rate of the decision is the important part to know. So, based on the rate achieved, we get two different category. One is the high decision rate detectors, another is the low decision rate detector. Remember, when we talk about the high decision rate detector, they are the basically passive matched filter based correlator architecture that we find in practice, and where the decision is made at the rate of the chip rate. So, within a chip duration, the decision is done. Huge circuit, this kind of processor, this kind of the detectors are hardware intense usually, and they take the decision on the out of sync code phase offsets between the incoming and the local code generation at the either at the chip rate, or it may be the integer multiple of this chip rate. And though they are fast enough, their accuracy is under question. There is lost of a lot of possibility to get a higher rate of false alarm in such detectors, and hence actually it is also a hardware intense circuit design it will be. Whereas the low decision rate detectors, they also do the same thing, but at a very low space, and then they are slower than the code chip rate, definitely that is slower than the code chip rate. And as such, many of these structures of this low decision rate detectors, who are the active correlator based architecture, will be involved here, and this low decision rate detectors, they are not also the hardware intense. Remember, this low decision rate detectors are also will give you very high performance in the detection level. I mean, false alarm rate will be less. And to complete this whole discussion, there is last kind of the detector types which we category in terms of your in sync and the out of sync hypothesis. I mean, there is a hit or there is no hit, synchronization is achieved or synchronization is not achieved based on the principle of the Bayes theorem or Neyman person kind of algorithms, where minimum probability of an error of the second kind, misdetection, for a given probability of error of the first kind, false alarm, they are all involved. And we will actually go in detail basically in the next module on the match filter based architecture to check also on the non-coherent kind of the detectors, and let us see how does it work in the next module. And now the time is to just put a summary on all the kind of the acquisition systems and the detector designs that we have discussed. And here is a tree which will help you to understand the different kind of the PN acquisition system based on the detector architecture, where the classification goes. We saw already that we have classically we can divide the detectors by coherent and non-coherent detectors. Then based on the rate at which the detectors are performing the acquisition, it can be a low decision rate as well as a high decision rate. High are usually match filter based passive correlators, and here the active correlators are involved. Then whether you are using a fixed dwell time or you are having a variable dwell time. If you are having a fixed dwell time, then whether you are using a single dwell time or a multiple dwell time. And further classifications are there over the multiple as well as the single dwell time, because in the single dwell time we have seen we have the classification based on whether we are using the full period of the code correlation, we are using the full period of the code for correlation, or we are not using it, we are partially using it. And multiple dwell times are also involved with the verification with the immediate rejection, or verification is with no immediate rejection is going on. And another branch which is based on the in sync or out of sync hypothesis based detection process, which involves the Bayes, name and person, or some other kind of the detectors. So, this is the with this we would like to end here in this module. With the understanding of the fundamentals of the PN code acquisition mechanisms available in the literature. For detailed study, one may, if you are interested, you may also search for some of the literature.